Right, let me solve another example. So this is an example of how to calculate the streamlines for what's called a stagnation flow. I'll explain what a stagnation flow is in a second. But suppose that like you have the velocity field that looks somewhat similar. Like so, it's u equals k times x, and v, the vertical component, is minus k times y, where k is some positive constant. Okay, so let's try and figure out what the streamlines of that flow look like, and then I'll explain why it's called a stagnation flow. So we use our definition of the streamline, dx over u equal dy over v, and plug in our expressions for u and v. In this case, we'll see that the k's, the constants that appear in u and v, cancel. And again, so like the way to handle this, so we've got basically a left-hand side and a right-hand side of the equation that are sort of begging to be integrated. But how you do the integration involves a little bit of creativity, but I would argue that it's usually best for these streamline problems to integrate from an initial point. So I'm going to integrate from x equals 0, or x0 and y0, like the initial locations, to some final locations, or some locations along the streamline x and y. So let me do that integration. So if you integrate dx over x, you'll get natural logs. So if you do a definite integration, that'll be natural log x minus natural log of x0. But when you are subtracting two natural logs from one another, you can combine that stuff inside the natural log as x over x0. So the left-hand side is natural log of x over x0, and then the right-hand side is just minus natural log of y over y0. From there, the rest is just algebra. So like I can move the right-hand side over, combine the natural logs, because then I'm adding two pairs of natural logs. So I would get natural log of x times y divided by x0 times y0 equals 0. I can, let's see, actually there's a mistake on here. It should say x times y divided by x0, y0 equals 1, because I need to exponentiate both sides. And in that case, I can solve for the shape of the curve. So it's y equals x0 times y0 divided by x, which is the equation of a hyperbola. So if I were to plot that, right, so if I were to plot a set of streamlines here, if I'm in the upper right-hand quadrant, that like if any of the starting points for my hyperbola are in the upper right quadrant, then x0 times y0 is a positive number. So the equation becomes y equals some positive number divided by x. So that'll trace out that series of lines. The starting point is a value that has a negative y and a positive x. Like the lower right quadrant will trace out an upside down version of that, and so on and so forth. So you can reason out like what the various curves are that make up the family of hyperbola. And then the next question is, which way does that flow go? So I'd like to be able to assign some arrows to these streamlines to point in the direction that the local velocity goes. To do that, basically just evaluate the velocity vector at some component, at some location along a streamline. So for example, anytime x is a positive number, you can look up at the top and it says that u, the horizontal component, is k times x. So if x is a positive number, that means that u is a positive number. So anywhere in the right quadrants, the horizontal velocity is a positive number and therefore points to the right. So you can assign a set of directionality to those arrows. Similarly, if x is a negative number, you can work out that the horizontal velocity is negative. So you can assign arrows to the left two quadrants as well. Talk about why this is called a stagnation flow. So any point where both velocity components, like u and v, is equal to 0 is called a stagnation point. It's called a stagnation point because, well, if the velocity is 0, the flow is stagnant. And so points where the velocity goes to 0 in a flow have kind of special significance. in aerodynamics and other aspects of fluid flow. So we'll see that, a low velocity leads to high pressures. And so a velocity of 0 is the lowest magnitude of velocity you can have. And so it always represents the highest pressures in a flow, at least in an inviscid flow. And so, generally it's a point of interest if you're trying to design something. So, in fact, a stagnation flow is a flow that's meant to describe an airflow approaching like a solid boundary. If you zoom in close enough to a solid boundary, it'll always look something like this locally. You can actually assign streamlines to the axes as well, so the lines x equals 0 and y equals 0. So if you can reason this out, for example, so if the starting point is anywhere where y equals 0, y not equal 0, then you can reason by looking at the equation for a hyperbola that the equation y equals 0 is a streamline of that flow.